In this video, I'll show you how algebra can be used to find the derivative of certain functions. So I'll continue with the example that we started in class, where we have a function f of x is x cubed, and we want to know its derivative, its rate of change, when x equals 2. So in class, we started by doing this graphically. I gave you a graph of this function. You found the tangent line. You just drew the tangent line at x equals 2 and estimated the slope. And then you also calculated this numerically using a calculator. But this example will be able to get an exact result without using a calculator. So we start by writing down the definition of the derivative. The derivative of a function at x equals 2 is the limit, as h gets closer and closer to 0, of this difference quotient. So this is just the change in the function, delta y, and this is delta x. So right, this is just the slope near 2. And we have a formula for the function. It's x cubed. So I can actually write this out. The limit as h goes to 0, 2 plus h cubed minus 2 cubed all over h. So in class, we took this and then plugged into a calculator for different values of h and got some numbers, and we said, okay, I think the answer is getting closer and closer to 12. What I'm going to do now is not go to a calculator, but instead simplify this expression, do some algebra on it, and we'll see a really nice thing will happen, and we'll be able to get an exact answer for the derivative without using a calculator or a graph. So the first thing I need to do is I'm going to have to deal with this cubic term. So I'm going to have to take 2 plus h and multiply it by itself 3 times. So I'm going to do that, and then I'll come back to this limit expression. Okay. So the task before us is to figure out what this is. 2 plus h cubed. I'm going to need to know what that is. So cubing a number means we multiply it by itself. And do it one more time. So we're going to have to multiply all of this out. So I'll start, doesn't matter, I'll start from the left and multiply these two together. And to do so, I'll have to distribute, or FOIL, first, outer, inner, last, as you might have learned it. And I'm just going to leave this alone. So let's see. 2 times 2 is 4. 2 times h is 2h. 2 times h is 2h. h times h is h squared. And then I still have this 2 plus h. So let me simplify this term in parentheses first. 2h plus 2h is just 4h. So we have one more bit of multiplication to do. I'm going to take 2 and multiply each term by 2, and then multiply each term in here by h. Again, distributing this out. So 2 times 4 is 8. 2 times 4h is 8h. And 2 times h squared is 2h squared. Then I'm going to multiply these 3 terms by h. And what do I get? I got 4h plus 4h squared plus h cubed. Okay, the last thing I'm going to do is group like terms. I've got 8. Then I want to get the h's together. I've got 8h and 4h. 8 plus 4 is 12. Then I've got a 2 and a 4, h squared. So that's 6 h squared plus h cubed. So we're done with the hard part, which is cubing out this expression. So now I'm going to take this expression, put it back into the definition for the derivative. Okay, so here's my expression for the derivative. It's this limit as h gets closer and closer to 0 of this expression. And this cubic term, well, we just figured out what it is. It's this thing here. So I'm going to take this and plug it in to this expression. So this whole thing is the limit as h goes to 0 of 8 plus 12h plus 6 8 squared plus h cubed. So that's this. Then I'm going to subtract 2 cubed from that. And 2 cubed is 2 times 2 is 4 times 2 is 8. This whole thing is still over h. Alright, so now a series of nice things happen. Note I have a plus 8 and a minus 8. So those go away. So I'm left with limit as h goes to 0, 12h plus 6h squared plus h cubed over h. Alright, and it may not look like it, but this is great news. It's great news because I can cancel some h's. In particular, I can cancel this one down here because there's an h here, here, and here. And I'm really happy that I'm getting rid of this h, because this is the h down here that's causing me trouble. I'd like to be able to evaluate the limit by just plugging in h equals 0, but I can't do it because it looks like I'm dividing by 0. But if I could somehow do some algebra to get rid of this, then we're going to be okay. So if I do that, limit as h goes to 0, so let's just look at what happens. I can cancel this h, this, and that becomes h squared. I need to divide each term by h. So then this gives me just 12 plus 6h plus h squared. So now we can evaluate this limit without using a calculator or a graph or anything. This just says what happens to this expression as h gets closer and closer to 0. Well, h squared is going to get closer and closer to 0 as h gets closer and closer to 0. And 6h gets closer and closer to 0 as h gets closer and closer to 0. I mean, you can really just, there's no danger, there's no division by 0. You can just plug in h equals 0. Those terms go away and you're left with 12. Because 12 is a constant so far as h is concerned. It doesn't change when you make h get closer and closer to 0. So this whole limit is just 12. And that's what we saw 2 other ways in class. So we've just shown that the derivative of the function f of x is x cubed at x equals 2 is equal to 12. So for many functions, you don't have to plug numbers in on your calculator to get the derivative. You can do some algebra stuff, manipulate things around so that this dangerous h goes away, and then you can evaluate the limit directly and get an exact number. So you'll practice this some for homework, and we'll do some more examples of this in class, and doing this is going to lead us to some of the shortcuts that we'll encounter in Chapter 3.